Hello everyone, welcome back to the channel. Today we're going to be talking about applying the backtest simulation project to index funds. So the first thing we're going to talk about is what an index fund is, both in the real world and in the context of this project. Then we're going to look at some code and the results that it produces. Then we're going to iterate on these two steps for a while because we have various different approaches that we can take, and we're going to try several of them out and compare them. Once we've gone through a few approaches, we'll summarise what we've learned, where we are, and finally talk about the next steps for the project. So what is an index fund? Well, in general, an index fund is an investment fund that people can buy into. Usually this will be something like a mutual fund or an ETF. Not always, but generally. An index fund is actively managed in a couple of different ways, and the core concept is that it attempts to track an index of some sort. Now, an index is a collection of investments that attempts to represent something, for example, the state of a market, the state of a sector, that kind of thing. And generally, these indexes are put together actively by experts, and that is the first way that you can think of these as being actively managed. The second aspect of active management is that someone has to buy and sell the assets to make the fund track the index. That's generally the fund manager. And you will always get some error between the fund and the index, and this is known as tracking error. Most funds will try and minimise this. Some will be willing to trade a bit of accuracy to gain extra profit. And often the buying and selling to match the indexes is done in a fixed period, which is known as a rebalancing period. So in the context of this project, an index fund is also an investment fund, but a virtual one. There's no real money involved here. Do not use this as investment advice, as I've said before. It will go spectacularly wrong for you. So in this project, these funds are algorithmically managed. This means we're going to write a piece of code that makes decisions about what to buy and sell at any given time. And this is because I am not a fund manager, I'm a programmer, and the objective is to learn about code for trading, not to actually pick stocks by hand. So our target index is going to just be the top 500 shares of the data set that we are using. The acceptable error we have is unknown, and in fact the target result is unknown. And we're going to compare multiple periods, and the effect here should be small. So I went and did some external research and found some studies that have looked at this, and it seems that monthly, quarterly and yearly rebalancing periods are all relatively optimal, and there's not much to choose between them. And these results will form the baseline of our future ideas. That's kind of the point of this. In this backtest project overall, we want to learn more about more active approaches to investment, but we need a baseline. We need to know what good looks like, and this will at least give us that. So let's look at the basic implementation then. So this is very, very simple. All we do, and this code gets called every rebalancing period, including at day 0, so it will be called to produce the initial buys, and then it will be called to manage every however many days. So we take the top companies, so we take all the companies in the market, we order them by price, and we take the top N, so in this case N will be 500. And then we calculate the value of this portfolio. We use that to work out how much money we can devote to each company, and then we simply work out from the price of each share today how many we can buy of each, and this gives us a list of target volumes. Once we have this list of target volumes, we sell anything where we have more than our target, and we buy anything where we have less than our target. Very simple. So what results does this produce? Well, growth happens. That is as expected, and that's good. One thing worth mentioning is that this kind of continuous growth isn't possible in the real world. You end up reaching limits around size of orders you can fulfill without affecting the market yourself. but we're not modelling that here, so this is a very simple attempt to model this. This is exploring concepts rather than real-world implementation details is the whole point of this project. So one thing that should be really obvious here is that the period does matter in this implementation. You have a 10-year rebalance seems to be optimal, a 50-year rebalance, which effectively means no rebalance, you pick your stocks at the start and just hold them, is also good but not as good. Yearly increases and everything else gets wiped out. And that, like I said from research I've done, is not what should happen. So this, well, we're going to look at some reasons why this might happen, and we're going to try and fix it and see where we get to. So my first thought here was that this could just be that the funds are too small and that individual fluctuations in prices of individual shares was having an outsized effect. This was simulating a $1 million fund, so I tried upping that to 100 million to see if that would help dampen out any effects from outsized individual items, and the results were identical, except these numbers are now 100 times larger, which you would expect when you started with a 100 times bigger fund. So that's a possibility eliminated. Negative results are still results, and people should publish more of them. This is my contribution. Yeah. Anyway, so if that isn't the case, what else could we do? Well, one thing I was wondering about was the weighting. So a lot of funds do something called price weighting. Now, what price weighting is a way of altering how much effect each individual share has. So, in the code we looked at earlier, each share got the same amount of money invested into it. With price weighting, what we do is we still work out how much cash we're going to have. Slightly different way of working it out, but comes to the same thing. And then instead of dividing that cash by the cost of each company, we work out how much it would cost to buy one of each company. We divide our free cash by the cost for one of everything, and that tells us how many of everything we can buy, and then we do that. So effectively what's happening here is we will end up with the same number of shares no matter how valuable each share is. And this means that the more expensive shares have a higher weight and a higher effect on our overall results than the cheaper shares. And how did this work out? It was mixed. So we have kept the two best results from before, and we have not met them at all. And we also haven't managed to save our lower rebalancing periods. We have no, we haven't. These have all done worse. Literally everything here has done worse. So why would I persist with this? Well, persist with this because several funds use this approach, so it clearly does have value. And also, you can't, with this stuff, you can't give up at the first setback. These things are exploratory. You will get them wrong over and over again. And a real skill in this kind of sort of simulation computing is knowing when to cut your losses and when to keep trying things. And here I wanted to keep trying things. So I was wondering what could be causing this, and one thing I thought about was, because we're buying an integer number of the whole market, we're going to have a lot of remainder of cash here. And so I wondered if that could be having an effect. So I decided to plot the amount of cash over time. So here we are, and as you can see, and this was on the 90-day version, as the fund plummets, the amount of cash left over increases drastically. And this to me is saying that certainly my idea is worth exploring further. May or may not be true, that this is the root cause, but it is certainly an effect that's happening. So let's have a look at what we can do about that. So we can do a partial rebalancing. So here, instead of buying an integer number of the entire market, we work out which stocks are not in the top slice, the index that we're trying to track, and we sell anything that isn't in that index. And then we work out what isn't in our portfolio but is in the index, and we work out the cost to buy an integer number of each of those. And this is a much smaller subset, which in theory should lead to a much smaller remainder. And as you can see, it does. So this is the same graph repeated. So now on a 90-day rebalance we actually make money instead of being wiped out. And our cash that's left over is much smaller. So in actual fact this orange line is the cash that's left over. Now the graph has rescaled itself because we have a higher final result, but the leftover cash at the end of the previous simulation was about 1 to the 8, which would be up here, and as you can see it's nowhere near that. I then plotted this with an even higher multiplier. I should mention the cash has multipliers on it to make it visible, otherwise you just have a line down near 0 somewhere. To see if we've eliminated the effect altogether, and we haven't. As you can see, we're still getting some level of increase in the amount of spare cash towards the end of the simulation. And again, we're still buying integer numbers, so that is a possibility. But the other possibility that occurred to me was that, before I go on to the other possibility, I just wanted to look at what happens on a 30-day. Sorry, I want to show you the overall partial. So we're still well below the best results of the naive approach, but all of our partial results are actually quite close together, which is good. That was one of our criteria. And if we just look at 30 days, which is the worst, and we compare it to the naive approach, definite massive improvement. So, as I was saying, I wanted to think about what might be causing this, and looking at the cash, we still have some cash left over towards the end. So that is one option, is that we might still be inefficient there, and we probably are. But something that occurred to me might be an even bigger inefficiency is something that happens with caching, which is called thrashing. So a good way to think about this is, if you imagine we simplify this down to we only want the very top share. And let's say we have enough money to buy 10 of the very top share, and we hold it for some period. And then we come to our rebalancing, and it's now not the top share. There is another top share, so we want to sell our top share and buy the other top share. Now, by definition, because we are no longer the top share, 10 of the new top share is worth more than 10 of our portfolio. So we can only buy, say, 9 of it, even though this is supposed to make us money overall, which it will, because we are expecting that new top share to grow quicker than if we'd held on to the now number 2 share. But we can only buy 9 of them, not 10. And then the next time this happens, we'll buy 8 and 7 and so on. So this works if the top share is going up and up, and the share that we are selling is going to plummet down. Where this gets to be a problem is where you have 2 shares that are close together that start alternating, and then that little inefficiency vastly outweighs any gain you make from making the trade. So I wanted to think about, is there an approach we can take that will eliminate that efficiency, or at least reduce the amount of thrashing that happens? So the approach I took was to do what's called buffering, and this is a way that you can do this with caches, with level of detail code, anything where things cross a threshold. And that is, instead of having one threshold, you have 2 thresholds with a little buffer zone in between them. And you only trigger when you cross one threshold, you trigger one action, and when you cross the other threshold, you trigger the other action. So what this looks like here is we now have 2 different lists of companies. The first one has this buffer, so it's twice as big as the actual index we're trying to track, and then we have the true index. And so we will now only sell something if it falls out of this larger group, which means we will sell things less often, and then we will buy anything that is in the original group. So results for this. Now, as you can see, cash down at 0 most of the way, which is what we want, and this the enhanced cash, the larger, the scaled cash, you can see is much smaller. But as well as being much smaller, it's also much more evenly distributed. It doesn't grow over time, and that's what we were looking for. That's what we were hoping for. And 90 days does even better than it did on the partial rebalancing approach we just looked at. So, what happens when we compare this to the naive approach? What happens when we look at this over different periods? So, over different periods, this is almost identical. The periods have very little effect, and this is great. This is what we want to see. This is what we were aiming for. This was one of our criteria for success, and I was thrilled when I saw this, and I thought, brilliant, done, finished. This is index funds. Great, that was easy. And then I plotted it against the best of the naive approach. Okay, now it doesn't look so good. So it's much more consistent, which meets one of our criteria, but it is massively outclassed by that other approach, which is unfortunate, really. So that's a shame. So what could we do here? Well, we could dig into this. We could try and figure out why and what we can do about it. But potentially, the neutral weighting is just more efficient than the price weighting over our particular data set. Now, I have a suspicion about what's happening here. Part of our data sanitization was taking out anything over a certain size, a certain value, because there was some rebasing going on, which was producing ridiculously large numbers. Unfortunately, the very highest stocks got taken out of the data set as part of that. Potentially, if I had an army of people to go and clean up my data for me, that would be worth looking at. But I think what might be happening here is that because those very valuable shares don't exist in this data, then the price weighting doesn't have the value that it would have in the real world. So that's my pet theory. I haven't dug into that enough to find out, for reasons I'll talk about later. So what I did do at this point was decide to go back to the neutral weighting approach. And I thought, what if we applied buffering to neutral weighting? So this is relatively straightforward. It's probably the most complicated we've done so far, but it's still not too bad. Again, we have a buffered set of top companies and a non-buffered set, and then we just calculate our portfolio that are in the buffered set, and then we work out which ones are available to top up any that are missing, and we do that effectively and divide the spare data, the spare cash over those companies. So what happens here? So we have a new winner. This actually outperforms the naive approach, which is a relief. It would have been horrible to think that I'd done all this work and then not managed to actually beat my first attempt. Doesn't beat it by a lot, but we go from about 3.5 to 4, so we're talking about 5%. It's not bad. Again, the 10-year rebalance is by far the most effective. The 1-year rebalance makes a little money but not a lot, and the others are all wiped out. So, what else can we do? So at this point, I was thinking about a technique from multiplayer gaming, where, and this is called Dead Reckoning, and what you do is, instead of sending the position of every player in the game every frame, you use the normal gameplay engine to run as if it was to run locally and update the positions in the future. but obviously there's input you don't know about, and so then you have to send errors from actions taken by the players that have affected the world in the meantime. And basically what this got me thinking about was we could apply this here by looking at the velocity of each share up to the current point where we're the current day when we're doing our rebalance, project out to the next rebalance, and use those projected prices to make our decisions, and then again use correct, and once we get to the next rebalance period, correct the errors. So what does the code for this look like? So again, one step more complicated than previous ones. So we have this code here. We have a number of samples, so we don't just want to look back at one point in time, we want to look back at a few points in time, and we also parameterize over a particular number of days per sample to look back. And what we do is we take the current price and we find the difference between the price in the past and the current price, and then we divide by the distance going backwards. We add this to an overall rate, and then we divide by the number of samples to get an average rate of change over those 10 samples, or however many you want to do. I found these two numbers to work quite effectively. We could do a linear regression with this. That just felt slightly overkill for what we're doing, especially because we know we have a fixed endpoint that we want to work towards. So I'm just calculating slopes towards today's price and averaging them, and it seems to work okay. So then we do the same top companies thing, but instead of the market, we do the projected prices to get the top companies. What does this look like? Well, we win again. This is now our best result by far. Nearly double the effectiveness of the naive implementation. And that's good. That's success. We still haven't, and a single year also is better. The shorter periods again have not moved. This hasn't worked. I would like to understand why, but I'm not going to. I'm going to stop at this point. So I did try one more thing, and I thought, what would happen if you combined buffering with prediction? That like buffering was better and predictive was better. So combining them, great, right? No. No. They cancel each other out. So the value of the prediction is that it sorts things, but the buffering then means that you're not eliminating things, so you're not actually using that predicted information very effectively. And so, yeah, they cancel each other out, which is unfortunate. I think you could probably do a very clever thing to figure that out, and that could be a future project. However, this is the last approach I'm going to take here. And the reason it's the last approach is the point of the exercise was to find a baseline, and I feel like we have found a decent baseline. We will now try and use more active strategies to beat this. This has turned out to be vastly more complicated than I expected. I thought index funds were relatively simple things, and I have been shown the error of my ways. This is an entire rabbit hole that you could spend years and years and years on, and I would actually be interested to do that, but it is not what we're trying to do here. What we're trying to do here is provide a baseline for other things and explore lots of different strategies around different ways of investing. So I've decided that this is the time to draw a line under this particular part of the project. So, in summary, indexes are very complicated, and it is very hard to know how accurate an index is. The results we got roughly match real-world expectations in several aspects. The growth over time roughly matches things like the S&P 500, the Dow, the FTSE. They all track similarly to ours. Certainly, order of magnitude is about there. There are interesting things. I mean, speaking of real world, there's one fascinating thing is what you can see in the data. You can see the .com bubble. You can see the 2008 crash. You can see the results of COVID. That is remarkable, you know. Like, that you can notice these real world points in this data is amazing, or I think it is anyway. So we have our baseline, and that's good. So I've identified some requirements. So if I was trying to solve these things, if I was trying to work out why this doesn't work, there's a few different, or why we have such a spread over the different rebalancing periods, which is the part that isn't working. There's a few different techniques I'd use. I would do differential debugging. So a buffered approach is effectively the same as the naive approach if you set the buffer value to 1. So you can run them against each other and you can debug them and see where they can where differences occur. And you can use that to try and find bugs and programming errors. And if you've seen my previous video on results, you'll know the difference between programming errors and user errors. And there's a difference between a strategy that is implemented wrong and a strategy that's implemented right but is the wrong strategy. So for finding those kinds of errors where we've implemented the right strategy wrong, that kind of differential debugging is really useful, and I've been doing a lot of that to get this far. So that's one approach. Another approach is to do the same thing but with a different eye. And you know that you're going to get different results with different strategies, but you can still compare them to each other, and that can spark creative ideas, even if you don't expect them to be the same and they don't tell you yes this is wrong or yes this is right. They can show you, oh, that's a funny thing that happened, oh, why did that happen in that one and not that one, and it gives you insights and sort of intuition. And I think that's sort of what I'm coming to, is that a lot of this kind of programming is not rote, it's not science. You can't engineer it. I'll come back to that. You can't follow a script. You have to just have some understanding of the domain, you have to have some sense of how code works, you have to have seen similar problems and sort of understand how they work and how to solve problems like that. But you actually can engineer this. And the way you engineer this is by making it as easy as possible to do those things. And these are the requirements I've identified for this framework to do that. It needs to run quickly. You need to be able to try an idea very quickly, because the more ideas you get through, the more likely you are to find one that works. It needs to be easy to try ideas, because the more time you're spending writing new ideas versus debugging slightly weird quirks of old ideas, the more likely you are to find a good idea. And it needs to be easy to visualize data, because again, visualizing is something that lets you spark off ideas and imagination and potential solutions. Something that I found incredibly valuable in my PhD was I wrote a real-time visualizer of the thing I was simulating, which was cells in the body, because it was a computational biology PhD. And just having that real-time visualization let me see what was happening. And in this project, being able to look at the graphs of the results and compare them has been such a powerful debugging technique. And I think that's probably what I'm weakest on in this project. I think I need to add more and richer visualizations. I think trying the ideas it works relatively well. The code is fairly customizable, fairly changeable. It seems to work quite well when I'm trying out new things. It seems to be quite readable. I'm generally in one function, which is the function I've been showing you various versions of over and over again. I've kept various versions side by side so I can compare them, and that's usually the only thing I'm having to change, which is quite good. And like I say, it needs to run fast. I think I'm there with that. Each run takes between 30 seconds and a minute. I think some of the ones with prediction, because it was doing lots of back sampling, took about a minute 10 at worst. That's entirely fine, I'm happy with that, but I need to keep it at that level. So, with those being sort of the learning outcomes from this exercise, let's look at some next steps. So the next thing I want to look at here is momentum investing. That's for this project. That's going to take a while. So I did have a big refactor in mind where I would cache off the data into a database and use Python to actually query that and do the graphing and things. I was planning that when simulation runs were taking 20-30 minutes. When they finally got up to 40 minutes, I just went and refactored them and made them faster. Like I say, they're now running 30 seconds to a minute, so that's fine. I don't think I need to do that now. I think I'm on to new strategies and active strategies, starting with momentum, which is a very basic one, but we'll get to that. The language project is coming along. That's probably the next video on the channel. So the language is called Flow. Don't have any actual language stuff working yet, but the runtime is basically done, so hopefully be talking about that soon. I'm very excited about language. I really want to get into actually implementing it because I've got some very exciting ideas that I want to try out and see if they're useful or if I'm just dead wrong. And then the RTS game, I've been doing some work on the map editor for that, and that is coming along, so hopefully I will have something to show you on that in the not too distant future as well. So once again, thank you for watching. I appreciate your time. I hope it has been useful. Take care everyone. I will see you in the next video.